Hello, good morning. Welcome to this next lecture on complex variables. If you recall, last time we had stopped at the Cauchy Riemann equations, which said that if a function f of z has a derivative at a point z0, then necessarily it is true that u of x is equal to v of y and u of y is equal to minus v of x, okay, where f of z was written as u of x comma y plus I times v of x comma y. Okay. So, Cauchy Riemann equations or conditions are necessary conditions, and necessary implies that if there is a derivative, if f of z has a derivative, that means it has an f dash of z at a point, then the CR equations must be satisfied. It's a one way theorem. Okay. If f dash exists, then CR equations necessarily are satisfied. The other way is not true. If we find that CR equations are satisfied, it is not sufficient to say that f dash of z exists. Okay. So, these are not sufficient conditions, but these are necessary conditions. Now, what makes a sufficient condition? In addition to CR equations, if the partial derivatives, in addition to the CR equations, if the partial derivatives ux, vx, uy and vy are continuous, then f dash of z exists. So, these are the sufficiency conditions. In addition to CR equations, partial derivatives ux, vx, uy, vy are continuous, then f dash x exists. Okay. So, let us look at some examples. Okay. So, we consider a nice function f of z is equal to z square. Okay. It is a nice function. We know it has a derivative at every point in the complex plane such that f dash of z is equal to 2 times z. It is already known. So, it is analytic, it has a derivative. Then we check are CR equations satisfied. CR equation satisfied, we check. Okay. Now, z is equal to x plus iy, and therefore z square, okay, is equal to x square minus y square plus I 2xy. Okay. Now let us check the CR conditions. So this function is u x comma y and this function is v. Okay. So let us do u of x. U of x is equal to twice x, okay. Then u of y is equal to minus twice y, okay. Then v of x is equal to 2y and v of y is equal to 2x, okay. So you see that ux is equal to vy, ux is equal to vy, and uy is equal to minus vx. So since this function has a derivative, necessarily the CR equations are satisfied. Okay. Now we take another example where it does not work. Okay. So next example is let f of z be equal to magnitude of z square okay. Again if we consider z to be equal to x plus iy, then magnitude of z is equal to square root of x square plus y square, okay, and magnitude of z squared is equal to just x squared plus y squared, okay, and I will just add this plus I into 0. So this part is u of x comma y and this part is v of x comma y. We have already seen that magnitude of z square is not a very well behaved function. It is not analytic, it does not have a derivative, okay. And so now we will check if ux is equal to vy. Now ux is here twice x and v, the function itself, is 0. So there is no question of vy, okay, vy is 0. Similarly uy is equal to twice y, and the other side vx is 0, okay. Therefore there is no equation, there is no way these can be equal. So CR equations are not satisfied, CR equations are not satisfied. Okay. Now we will move on to what are called analytic functions. Okay, we will move to a next topic called analytic functions. Analytic functions. Analytic functions. Okay. A few definitions will come over here. So I will partition the space this way, it seems convenient. Okay. Analytic functions. So here are a few definitions. So there will be some writing to do. Okay. A function f of z, f of z of the complex variable of the complex variable z is analytic in an open set if it has a derivative at each point in that set. If f is analytic at a point z0, it is analytic in the neighborhood of z0. Okay. So here a few cases arise for our better understanding. So one is a function can be differentiable at a point but not analytic at that point. Okay. We saw this case just earlier. This function f of z is equal to magnitude of z square, okay, didn't have a derivative anywhere except at z equal to 0, okay, and nowhere else does it have a derivative. So this function is differentiable at one single point z equal to 0, but not analytic at that point, because in the neighborhood of z0 it does not have derivatives. Okay. The other case arises, okay, if a function fails to be analytic at a point z0, but is analytic in every neighborhood of z0 So it is not well behaved at z0 only, around it is well behaved, then then Z0 is called a singular point, is a singular point of f of z. Okay. We will see such cases in the future when we solve problems. Okay. So, that is as far as analytic functions is concerned. Now, we moved to a few definitions which are required. Okay. So, here these are the definitions. So, let us call this a few useful definitions. Okay, what are they about? They are about curves, arcs and contours. Okay. Now, let us see what is an arc. Okay, what is an arc? A set of points z is equal to x comma y, okay, or this is also written as x plus iy. Okay, I have briefly introduced a new notation. The complex variables are written this way also. So, a set of points x plus iy is called an arc, okay, if x is a function of this variable, real variable t, and similarly y is a function of the real variable t, and t extends between a and b on the real axis. Okay. So, such a set is called an arc. Okay. T lies increasingly between a and b, x is a function of t, y is a function of t, then z, which is x plus iy or x of t plus iy of t, is called an arc. Okay. Now, x is equal to x of t and y is equal to y of t are continuous functions, must be are continuous functions of t. Okay. They can't be discrete functions of t. Okay. X is a continuous function of t, y is a continuous function of t, then z is called an arc. Okay. Now, this arc, it is a simple arc, if it does not cross itself, Okay. However, the other case, when C is simple, that means it does not cross itself, but yet except that the end points meet, that is z of A is equal to z of B, okay. Then C is called a simple closed curve, a simple closed curve. Okay. Then the next definition, okay. We have not said anything about how x dash and y dash, the derivatives of x and y with respect to t behave, okay. So the next definition is, if x dash of t, that means the derivative of x with respect to t, and y dash of t are continuous, the derivatives are also continuous throughout, okay, as t varies between A and B, then C is called a differentiable arc, okay. We will take some examples a little later so that this becomes clearer, okay. Now further, if z of t is a differentiable arc, as above, is a differentiable arc, is a differentiable arc, and further, okay, further this quantity magnitude of z dash of t does not go to 0 anywhere in t, as t varies from A to B, this quantity never goes to 0, then the tangent x dash t plus I y dash t refers to the tangent, then the tangent turns continuously, okay, and such an arc is called smooth, okay. Such an arc is called, such an arc is called a smooth arc, okay. Smooth arc will be very commonly, we will come across it very commonly in our course, okay. So z dash t magnitude going to 0 is a rare case, it is kind of a pathological degenerate case, so it rarely happens. So we will be dealing mostly with smooth arcs, okay. Further, okay, the next definition is a contour, okay. So you will see how the smooth arc features in a contour. A contour is a piecewise smooth arc, okay. Piecewise is the most useful part of the set of definitions. A contour is a piecewise smooth arc, So, just to give you a okay, let me finish this. Consisting of a finite number of a finite number of smooth arcs joined end to end, joined end to end. Okay. Then what happens is z dash of t, hence z dash of t becomes piecewise continuous. Piecewise continuous. Continuous. Okay. So, we will take a look at this in the next page. So, if I have a contour which is made up of smooth arcs joined end to end, okay, okay. So, these portions are smooth arcs, these are smooth arcs, okay. So, that the tangent turns continuously, tangent turns continuously on them. Here also the tangent turns continuously, okay, the tangent turns continuously, whereas at these kinks, okay, the derivative z dash t will take jumps, okay. So, z dash of t is now piecewise continuous, it is continuous on these smooth arcs, but at these kinks z dash t is piecewise continuous, it takes a jump, okay. Further to that contour definition, when the two end points, the two end points, okay, it so happens that z of a is equal to z of p, when the two end points meet, then we have what is called a simple closed contour, okay. So, this is another contour we will come across, okay. We will come across this quite a bit, and I will use this acronym, I will use SCC, it will stand for simple closed contour, I will not expand it all the time, okay. So, let us take now an example, let us take an example, okay. Suppose I have z, okay, it is parametrized through x alone, okay. So, I have x plus ix when 0 less than equal to x less than equal to 1, and it is equal to x plus I, okay, when 1 less than equal to x less than equal to 2, okay. So, how does this thing look in the complex plane? Okay, I have 1 here, I have 2 here, this is real axis, okay, this is the imaginary axis, okay. Now, z, my curve is, I am sorry, why did I write 2 here? So, it looks like x plus ix, okay, this is x plus ix. So, y is equal to x, okay, and then that is happens till 1, it happens for values x between 0 and 1, and between 1 and 2 the imaginary part remains constant and we get this, okay. So, this is the example of a simple contour. So, this part is differentiable, it is a smooth arc, this part is differentiable, it is a smooth arc, and we have joined them end to end, it is a simple contour, okay. So, we will continue with these ideas in the next lecture. I will close here. Thank you.